Hi, I'm Yimeng, and I'll be presenting our work, Starting the Path to a Million Client Server. This work was done when I was a PhD student in Georgia Tech. The work is motivated by the need of scaling up of end hosts in data center. With the increasing traffic demand, a single host in data center needs to serve not only much more data, but also a larger number of flows. This is further advanced by the use of virtualization techniques. Virtualization allows for sharing of resources in public clouds, hence it is heavily used, so a single host can serve different types of services. So there are reports showing that a single host may serve up to 150 virtual machines and up to 50,000 flows. We believe this trend will continue, and a networking stack may need to serve more traffic flows. So from a networking stack, it needs to cope with hundreds of thousands of flows. Then a next question would be, what are the bottlenecks arises when a server needs to scale? We believe this question hasn't been fully answered yet. So much of the attention in the previous work was paid to the scalability problem when a server needs to serve more traffic, but not on the number of flows. The previous work mainly focused on improving the reception path efficiency, but our measurement work find that the transmission path can also become a bottleneck when there are a large number of flows. So the limited work on the transmission path mainly focused on packet transmitted per second, not on the number of flows. Also, it really focused on a specific networking component like congestion control or the scheduling component, and they did not consider the complicated interaction between different layers. So our work is a measurement study. We evaluate the scalability of the network stack as a whole at hundreds of thousands of flows. Our work gives a broader category of scalability concerns. More specifically, our contribution includes a measurement study on Linux. We identify the bottleneck arises when a server scales to hundreds of thousands of flows. Although the main measurement is done on Linux stack, we carefully examine each of the issues we identified and study whether it is an implementation problem that is specific to Linux, or there are more fundamental problems and can apply to other platforms as well. We'll also discuss whether the existing solutions can mitigate the problem effectively with large number of flows. The experiments are mainly performed on 2 servers connected with a 40 gigabit per second links. We use a traffic generator to generate different number of TCP flows, ranging from 100 to 300,000. Here's a summary of our findings. We categorize the problem in 2 different types. The first is admission control. Admission control decides how frequent a flow can access a stack or layer, and it also decides how much traffic can be sent in each access. The admission control problem usually involves multiple layers. The issue we found include the inefficient back pressure and scheduling, the overpacing problem, and oblivious hardware offload. The second type of problem is per packet overhead. So this is more platform specific. So on the Linux stack, we found some of the data structure are not efficient enough. And also the log contention and cache pressure can become a bottleneck with hundreds of thousands of flows. So for all the issues we identify here, we believe that only the log contention have been fully investigated. The other 5 problems, it either needs a better solution when there are hundreds of thousands of flows, or the problem is only partially solved. Because of the time limitation, I'll only talk about the first issue, inefficient back pressure and scheduling in this presentation. So here's a figure of the different stacks in the transmission path. So our focus here is the scheduling component. In our work, we mainly consider the field queue. In our evaluation, we also consider other scheduling policies, but here I only talk about field queue. The field queue tries to ensure the fairness in the decrew process, so each flow can get a fair share of traffic getting through. But we found that field queue starts to perform less efficient when there are more than thousands of flows. So the cause of the problem is not on the field queue itself, but because of the interaction in the layer above, that is in the NIC and ring buffer, and also in the layer above, that is the TCP layer. So first, although the field queue tries to ensure fairness in the decrew process, the batching in the NIC and in the ring buffer make it less efficient. The second problem is the admission control from the TCP layer to the field queue. So the field queue cannot control how frequent TCP flow can actually into a packet. So it is possible that a flow can hardly ever get a space when competing with other flows. So to address the fairness problem, we need to have a better admission control from the layer above, and we need to have a better back pressure from the layer below. Our study includes the evaluation on the throughput, the CPU utilization, and also the latency. We also have function profiling to find the inefficient data structure and the cache problem. So for this presentation, I'll only talk about overall stack performance. We mainly look at the throughput, CPU, and latency. We can see as the number of flow increases, the CPU utilization steadily increases until it becomes the bottleneck. But here on the results, on the latency, we can see that the latency is actually already increasing before the CPU becomes the bottleneck. We found that at different stages, the main bottleneck that leads to the increase in latency is actually different. So for the more detailed results, we have micro benchmark results in our paper. The main takeaway here is that design a networking stack and scale to a large number of flow is challenging. So there are some new challenges arises. And also we need to reevaluate the existing solutions to see if it still works effectively with hundreds of thousands of flows. And also to design a scalable networking stack, we need to consider the complicated interaction between the components and layers. So only try to optimize a single components may not solve the problem effectively. That's all of the presentation. Thank you.